I want to go over the definition and some properties and examples on the Laplace transform. I know that many of you have dealt with the Laplace transform before in either a math class or possibly in a linear systems class. In this class, we take a less theoretical and more practical approach, looking strictly at the Laplace transform and what it can do for us when solving circuits. So today, when I go over some Laplace transforms and how they're derived, as well as some properties of transforms, I'm doing that in mind with these are some of the ones that we will use most frequently in analyzing circuits. So in engineering, we use the single-sided transform because we're basically assuming we're modeling some kind of system whose response is desired for times that are greater than or equal to 0. So the equation shown here is the equation for the single-sided transform. And because of this, you need to be very careful when you use tables not associated with your textbook or with the ones I give you, because oftentimes tables, you just have to be sure that you're looking at a table of the single-sided transform, because there is a transform that runs from negative infinity to infinity. It is not one we use in engineering, but you may or may not have seen that in math. The other thing to keep in mind is that the transforming function itself is this e to the minus st. Now, transforms are common, and they're commonly used in science and engineering. They're basically primarily utilized to either weight a function under integration, or they're used to transform the variable from a form that is in an equation that is perhaps difficult to solve to a variable that is less difficult to solve. And that's one of the primary reasons that we use the Laplace transforms in circuits, is that it handles derivatives in such a way that a differential equation is transformed to an algebraic one, which makes the solution much easier. Now, this s in the numerator is the variable that you're transforming to. So you take some input function f of t, you put it through this process of integration, and what you end up with is a function f of s, where s is defined as sigma plus j omega, and it's known as the complex frequency. So because s has both a real part and an imaginary part, and your transforming function is e to the minus st, then basically your transforming function will have an e to the minus sigma t part and an e to the minus j omega t part, meaning it can represent both exponential decays as well as oscillation in the time domain. So let's just look initially at how we might take the transform of some simple functions, and we'll start with the Laplace function or with the impulse function, because this is also a way to review impulse functions. So to find the Laplace transform of the impulse function, first of all, this script L with the curly brackets is our way of indicating we're taking a Laplace transform. It's going to give us a function of s. So we take whatever's in the brackets, which in this case is the impulse function, we plug that into the integral, and then applying the shifting theorem of the impulse function, we know that basically this integral is going to be e to the minus st, evaluated where t is equal to 0. So we have e to the 0, which is equal to 1. The step function is another fairly simple function that we can take the transform of. We take the step function and plug it into the integral. The step function is equal to 1 for t equals 0, and it's equal to infinity. It's equal to 1 all the way to infinity. So we basically, because of our integral limits and the fact that the Laplace transform is single-sided, we can just replace u of t with 1, which means we're integrating e to the minus st from 0 to infinity. When you plug that in and evaluate through the limits, you get 1 over s. These two transforms, the fact that the transform of the impulse function is 1 and the transform of the step function is 1 over s, really are transforms that you should know by heart. This is a very simple and common transform throughout engineering. So these should be some that you really should not have to look up on the tables. Another example would be to find the Laplace transform of an exponentially decaying function. So I have my equation here, my transform that I'm going to take is e to the minus at u of t. So I want to talk a little bit about why we put the u of t here. In the applications for which we're going to be using the transform, as we said, we're using a single-sided transform. E to the minus at exists for negative times. So we can't really take a Laplace transform of any part of e to the minus at except for the part that exists where t is greater than or equal to 0. So in order to convey that, we put the u of t here to represent that this function does not exist for t less than or equal to 0. So we can just once again let u of t go to 1, and in our integral we have e to the minus at times e to the minus st, which is essentially the same thing as what we just had. We can group s and a together, and when we do that, our integral comes out over, once we plug in the limits, comes out to be 1 over s plus a. So once again, the statement here is what I just said, that we multiply the exponential function by a step, done so we can use the single-sided Laplace transform. And all of the Laplace transforms that are available in your textbook and on most websites, even if they don't write the u of t, it is generally assumed or implied that it is there. So it's important to understand that. If it is not a single-sided transform table, it will often say it is double-sided. Okay. So here's another example. This is one that I worked out a little easier to just work it out by hand. This is an example of the Laplace transform of the sine function, sine of omega t. And one of the reasons for me to include it here is, and I know that many of you have had linear systems, and so this math should be fairly familiar to you, but it's a pretty common technique when we have a sinusoid, and when we have a sinusoid, to replace that using Euler's relation with the difference of sum or difference, depending on whether it's sine or cosine, of e to the j omega t. So here for the sine, we have e to the j omega t minus e to the minus j omega t divided by 2j. So this is the substitution that we use for the sine function, and the reason is it's significantly easier to integrate. So our Laplace transforming function e to the minus st is still here in the integral. And what occurs between the line that we're currently looking at and the next line is some algebra, where we take the minus st in the exponential and the j omega t and the minus j omega t in the expression for the sinusoid, and we combine those, which means that our exponentials now look like this. So once again, as far as the integral is concerned, because the integral is over time, to the integral, s and omega just look like constants. So we're integrating over t, which basically gives us the same result that we had when we integrated e to the minus s plus at. So you can see we pull the 1 over 2j out. The minus sign comes from the fact that when we take the integral of e to the minus constant times t, we generate a minus. And then these two terms come from taking the integral from 0 to infinity. So when we do that, do some additional sign simplification, and then taking a common denominator of s minus j omega times s plus j omega, we end up with s squared plus omega squared in the denominator, and the simplification from the common denominator puts the following in the numerator. A little bit more algebra shows that the two s terms are going to cancel out, the j's are going to cancel out, and basically going to end up with this expression right here, where omega was the frequency in radians per second of the sinusoid, and s is now our complex frequency, and it is now the variable in this equation. So it's a variable transformation from a variable of time to a variable of complex frequency. If you repeat the same process for the cosine function, the substitution here for Euler's formula is slightly different. It has a plus sign and a 2 in the denominator. And so if you work all the way through that and do the algebra, you find that the cosine ends up being very similar form. The only difference is you have an s in the numerator rather than an omega. So that's the Laplace transform of a sinusoidal function. So I'm going to show you some tables here. I took these not out of your textbook, but these came out of Wikipedia's page on the Laplace transform, so here is the reference for that. Your textbook also has a very good table. I just wanted to provide you with another option. So these tables were taken under the Creative Commons license from the Wikipedia site. And so basically what you see here is you have one column called time domain, and you have another column called Laplace domain. And so what this represents is the time domain represents a function in time, and the Laplace or S domain represents a function in S. So what has happened is somebody has already tabulated for you the Laplace integral, and that's very nice because most of the functions that we work with in electrical engineering will fall into something that is given in this time domain column. So for example, we have an impulse function, we have a time-shifted impulse, we have a unit step, we have a time-shifted or delayed unit step, we have a ramp, we have a polynomial term, t to the n. Notice that they're all multiplied here by a step function. There is a t to the n, e to the minus alpha t. There is a t minus tau to the n, e to the minus alpha t minus tau, u of t minus tau. And all of those then have their corresponding Laplace transform here in the Laplace column. I want you to notice something really quickly. If you look at this one right here, where we have the delayed nth power, and this could be anything. So notice that our time variable is not t, it's t minus tau. And in order to apply this formula shown in this table, everywhere you have a time variable, it has to be t minus tau. So in order to apply this Laplace transform formula, you have to have all of your t's going to t minus tau. That allows you then to take care of that time shift by this e to the minus tau s. And we'll talk a little bit about that later. This bottom one is exponential decay, which we already showed earlier in the lecture. This is exponential approach, so that would be if you have this, you're approaching, in this case, 1. And so you see the Laplace transform of that. Here's your sine, your cosine. Hyperbolic sine and cosine we don't really use much in electrical engineering in most curriculum. You begin to see some hyperbolic sine and cosine in electromagnetic fields. Usually it is a geometric description, not a temporal one. But nevertheless, they're given here. You notice that only the hyperbolic sine and cosine is the only time you have this negative sign in the denominator. And given that these are functions that are pretty much unbounded, they're typically not functions that we see as functions of time in EE. So you just won't see that often. So if you are analyzing a circuit and you come up with negative signs in your denominator in an S polynomial, that is probably a mistake because these tend to not be the kinds of functions that we would see in a circuits class. Finally, you can have an exponentially decaying sine or an exponentially decaying cosine, and the corresponding transforms for that are shown in this table, in this column. Okay, the other thing that you sometimes see is you sometimes see properties of the unilateral Laplace transform, and unilateral is just another term for single-sided transform. So we can see properties of the single-sided transform. Basically, the main property is we have property of linearity, meaning the weighted sum, the transform of the weighted sum of two functions is the weighted sum of the transform. So you take transform of f of t, transform of g of t independently. If they're weighted, the constant comes right through the transform process, and you can prove that using very basic rules of integration. If you have multiplication of a function by time, so f of t is some function like cosine of t or e to the minus t or whatever, if that's multiplied by time, that translates, if you take the Laplace transform of f of t and you get f of s, you can handle multiplication by time by taking its derivative and making it negative. So you take the first derivative of f with respect to s and multiply it by a negative sign, and that's the same as if you had tf of t. That's the transform for that. And that can be generalized for t to the n, and here is the formula. It's the nth derivative of the function in the Laplace domain, and then there is a negative sign that is negative for odd orders and positive for even orders. We can flip that around and do the derivative in the time domain, and the derivative in the time domain in the frequency turns out to be multiplication by s and then a subtraction of the initial condition. And I believe this is one of the ones in the notes that follow that I actually prove. The second derivative I don't think we prove, but the second derivative basically follows the same pattern. Notice that in the first derivative you have one initial condition. In the second derivative you have two initial conditions, one on f and one on f prime. In the nth derivative you will have n initial conditions, and so you can generalize this formula to what is shown right here, where you have multiplication by s to the n, and then you subtract off a series of initial conditions generating a polynomial in s for those. Frequency domain integration is division by time. This one is not used a super big amount in our class. Time domain integration is used. Time domain integration is basically integration in the time domain is division by s in the frequency domain. Frequency shifting, so if we have f of s minus a, that came from taking a function f of t that would generate the transform f of s and multiplying it by e to the at. Time shifting, I have some function, and instead of a function of t, it's a function of t minus a. That comes across as whatever the transform of f of t would have been times e to the minus as. The one thing that I want to be sure you get is, notice the Heaviside or step function has also been time shifted, and it's been time shifted by the same amount. So a lot of times you may see a function of time and it may be multiplied by a shifting step function, time shifted step function. What you're going to have to do there is you're going to have to figure out how to get the function of time to look like it has the same time shift, because the step function is a definition and it can't be manipulated or changed. But the function, we can sometimes go in and take advantage of some algebra or some trig identities, and we can get it to look like the same time shift. Time scaling is shown here. This is one that I personally don't use a whole lot in my class. Okay, I really want to draw your attention to this line right here on multiplication, because I can tell you from past experience that in my classes, probably a third of people miss this concept. So multiplication, the transform of multiplication is not multiplication of the transforms. So in other words, f of t times g of t is not equal to f of s times g of s. It is equal to the convolution of f of s, g of s. And so do not try to use multiplication of f of s and g of s if you have this given as a problem. And then finally, the property of convolution. This is really important because it allows you to go from a system in the time domain where everything has to be convolved, to a system in the frequency domain where transfer functions are multiplicative. So convolution in the time domain goes to multiplication in the frequency domain, and this is huge. This is part of what allows us to easily analyze things like filters for their outputs, because we can do this. We can basically stack systems back to back and multiply their transfer functions together. So at this point, before getting to looking at some practical examples of some of this, I want to stop the video and allow you to take a break before watching us discuss some examples.